Hi, everybody. Welcome this morning. We're going to give it about 1 minute while people jump on, and then I'll introduce our speaker, Mike Pritchard, and we'll get going. Everybody, we're going to give it about 30 more seconds while people join, and then I'll introduce our speaker and we'll get going. Good morning. Okay, well, I am going to get started. We're so happy to be able to host what I think is going to be our last public lecture of the remote era, at least we hope so. But I'm glad many of you could join us this morning. So this is our public lecture series. As you may know, this month, through various events and news stories, we've been focusing on data science and machine learning in the physical sciences and how it's been utilized within the School of Physical Sciences. And today, we're going to be hearing about next generation Earth system modeling, so climate change type modeling in the machine learning era. And this is really well aligned with the history of this school. We have the first Earth System Science Department in the country that was established by Ralph Cicerone, who was a former dean and chancellor and president of the National Academy of Sciences. So the legacy in this area at UC Irvine is deep, and we're very proud of it. And as you'll see today, we continue to lead the world in not only answering important questions, but utilizing next generation techniques to get these answers. So today's speaker is Mike Pritchard, who is an associate professor in the Department of Earth System Science here at UC Irvine. As an interdisciplinary climate scientist, he's interested in understanding how the planetary water cycle works and how it may change in the future. He uses a blend of next-generation global atmospheric simulation algorithms, theoretical dynamics, and high-performance computing. And recently, he's been utilizing tools in the data sciences such as deep machine learning and neural network-assisted dynamical inquiry. He is a DOE Early Career Award recipient. So if you don't know what that is, that's a big deal. It's hard to get those awards, and it means you're sort of pegged as a future star. And he co-leads a national working group about emerging data science tools for studying climate variability and climate change. So we could have no one better to talk to us about this subject today than Professor Mike Pritchard, and I'll hand it off to you, Mike.
Thanks so much for the nice introduction, and it's a pleasure to be here with you this morning remotely. I'm excited for this to maybe be my last remote lecture too. That would be great, but we'll see. Okay, so let's dive in. I want to start by just acknowledging some friends and colleagues in this work. My close conspirator, Pierre Gentine, a professor at Columbia, who brought me into this machine learning topic. And then some important UCI scientists, Tom Buechler, project scientist in my group, soon to be faculty in Lausanne. Griffin Moore is a bright PhD student. Jordan Ott in the computer science department, who's advised by Pierre Baldi. There's a really collaborative work between the Earth System Sciences, and Stefan Rask, who came to visit me. So let me introduce myself a little bit. I have sort of two research interests. Half of me is interested in questions about the planet, big picture questions about how clouds might reorganize, open questions about the dynamics of our planet's atmosphere and how it couples to the ocean processes. Half of me is interested in how things are going to change in ways that matter to people as we perturb the system in a very unfamiliar way. The fate of rainforests, regional water cycles, future river flows. But I find that these two research interests often intersect on this common issue of confronting turbulence. And that is really what pins my interest in machine learning. So let me introduce some of the tools we use in my group. We use standard climate models, the same type of climate models that the IPCC internationally uses to predict the future in 100 years. We use sort of research tools too that relax assumptions about cloud physics, super parameterized climate models. I'll tell you more about that in a moment. And then machine learning to try to emulate and understand the cloud parts. And because of these kind of technical interests, we like to explore a lot of supercomputers around the country. So there's amazing computing architectures at the Department of Energy, some of the world's best computers at the Texas Advanced Computing Center, and down the coast at the San Diego Supercomputer Center. There's just amazing hardware in this country. And so because of that, we also sometimes get involved in the actual development of climate models as well. So diving into the code and helping co-build them. Okay, so let me just give a primer on what is a climate model. Okay, so I want to start, what is it not? It's not a statistical model. It's not curve fitting. It's not extrapolating measurements from the past into the future. It's a deterministic physical model. Solves equations of conservation of energy and momentum. It's a weather model. The same differential equations that predict weather at the NOAA and the National Weather Service are inside the heart of climate models. But weather is an initial condition problem, whereas climate is a boundary value problem. So, things that affect the weather statistics, climate like the sunlight, and how it varies with an 11-year cycle, and volcanoes that come and go, and the CO2 that's been changing a lot over the last 100 years are the boundary conditions that create climate predictions. Yeah, you can think of it as Newton's second law, F equals ma, for a compressible fluid on a rotating sphere with radiation, thermodynamics, and phase transitions. Here's the anatomy of a climate model. There's atmospheric component and an ocean component and land component. This is an old figure, but this anatomy hasn't changed much. But I want to draw your attention to the top in the atmosphere. There's equations of motion, very principled things, and then there's parametrizations of turbulence and parametrizations of clouds. I'm going to define this word parametrization for you shortly because it's important. And it has to do with the fact that climate simulation means modeling across immense scale differences. We want to study the planetary scale circulation. We can actually write down the equations that are relevant to predicting very large scale planetary waves that happen in the atmosphere that control mid-latitude weather. But we also need to study how they interact with smaller scale phenomena like cloud dynamics, like thunderstorms you see out your airplane window, and radiation, so details about how radiation flows through the droplets and the ice crystals that are inside of a cloud. And those physics are not resolved, they're parameterized. So parameterization is this sort of necessary evil of climate simulation where we don't have infinite computing power. And so there's a mesh resolution, and climate models get higher resolution every year, but not fast enough. And so there's always a subgrid that has to be somehow approximated empirically or physically. And here's an example of a toy cloud dynamics model that's famous from the 1970s, and we inherit still a lot of its legacy, that assumes that the unresolved clouds, whose geometry is unknown, we can assume that they behave like an ensemble of elements with different heights, and that maybe the ensemble obeys some overall thermodynamic rule that the job of the clouds is to deplete convective available potential energy at some rate. That's one way to make a toy cloud dynamics model. And we also have toy microphysics models to handle how fast water vapor partitions between liquid or vapor forms depending on the available ice crystals or droplets around. But these are toy models. And so this brings me to superparametrization. Superparametrization means more than parametrization. And it basically means replacing the toy cloud dynamics models with a simplified but much more explicit cloud resolving model in every grid column of a global model. So imagine 10,000 two-dimensional cloud resolving models that have enough horizontal resolution and take a short enough time step and include enough nonlinear turbulent terms in their governing equations to actually produce individual cloud elements, but just for a small sample of the planet in each grid cell of a host model. Kind of like the way an opinion pollster will sample a small fraction of a state's population and extrapolate its behavior to the whole.
Hey, Mike.
Yeah.
Sorry to interrupt. I have gotten some comments that if it's possible for you to get a little closer to your microphone, people are having a little trouble hearing. Sorry about that.
Thanks. My bad. Okay, I'll try to speak over to the laptop here.
Thanks.
All right, cool. Let me know if it persists.
Okay.
Okay. So my interest in machine learning is because I would like to parameterize less. I would like to be less toy-like about these physics. So superparameterization is one way to do that. It's a way to become more explicit about the cloud dynamics and the thunderstorms, but there's always still a scale regime where we have to parameterize, and there's always details like microphysics that are uncertain and approximate in climate projections. Okay, so that's the primer. Let me give you a roadmap for this talk. The first part I want to motivate deep learning emulation. Tell you why I think turbulence matters so much, talk about some details about supercomputers. And then I want to tell you a story about some work we did trying to use deep learning to emulate cloud physics and what really got me interested in this. And then what I've learned in doing it by talking to computer scientists, the challenges our community is facing as this new data science tools are disrupting the business of climate simulation. And then the future, some topics I'm interested in working on soon based on these conversations with computer scientists. And so let's start here. A little more motivation, okay? Back to the scale problem. This is another way to look at the basic problem facing climate scientists of having to simulate across 10 orders of magnitude in space and time. This is a log plot, time on the y-axis, space on the x-axis. Every first year atmospheric scientist, grad student sees a plot like this. And up here is the slow, on the yellow box at the top right, that's the slow large things that a global climate model can capture. Lots of important things: El Nino, seasonal cycles, monsoons, planetary waves, tropical cyclones. But you have to draw a cutoff somewhere. If you want to simulate the whole planet for 100 years, that's all we can resolve explicitly, and the rest has to be approximated. We have other modeling tools, though, like CRMs, the red box, cloud resolving models that can resolve for a small patch of atmosphere for a limited period of time. Details like tornadoes, thermals, turbulence. NOAA uses these for hurricane forecasting. And then on the blue box, my main interest, large eddy simulations. And these really can do justice to the small scale physics. So they take that really fine grid resolutions, like 10 meters. They take unbelievably short time steps, like 0.1 seconds. And therefore, you could never use them to simulate the whole planet, but you can use them to study the details of actual cloud formation, actual turbulence, and get process level understanding. And it might not be obvious at first why handling those small scales meticulously really matters for the big picture. So let me just be careful to motivate that for you. This is really what's driving my interest in machine learning. I'll give you 2 lines of motivation. The first has to do with low clouds. Okay? We're lucky in Irvine. We live next to one of the most amazing, beautiful low cloud decks on the planet. There's a few of them off the coast of Peru, Western Australia. You can see this from satellite geostationary imagery. Here, you're looking down off the coast of California at this low cloud deck, this bright patch of atmosphere, and just look at its complexity. It's constantly transitioning between these open and closed cells with fractal reorganization, and all the beautiful complexity of the turbulent processes that create those spontaneous transitions has to be approximated in climate models because it's sub-grid. But it's clearly there. It's happening every day in nature, right? It's beautiful to look at. And we know a lot about these cloud decks from studying them for decades with planes and boats and numerical models devoted to small patches of atmosphere. We know the processes that sustain them. We know that turbulent mixing is essential, and fine scale eddies acting across that sharp interface of cloud you might have seen if you've flown to Hawaii out your airplane window for half the flight. And we know how to simulate plausible dynamics of these low cloud simulations. If we take a computing cluster and apply it to a small patch of atmosphere, we can produce simulations like this, which shows a classic transition of an unbroken stratocumulus cloud as it advects, as it flows over warmer waters, and it transitions to a cumulus under stratocumulus, a new form of cloud organization that the system prefers. As you look down on the top of the simulation at the end, you'll see that that new form of cloud organization after warming, after the air has advected to warmer temperatures, is also darker and more broken. There's more exposed sea surface temperature. This is a more absorptive situation. And this is why the brightness of clouds related to their organization matters so much. When shallow clouds reorganize, so does the top of atmosphere radiation. Any planetary scientist or astrophysicist will tell you that the reason behind all the ocean circulations, all the weather circulations on any planet is fundamentally due to a differential radiative forcing. And on our planet, because we have these amazing clouds, they interact with that radiative forcing. So they create weather patterns and circulations by virtue of their brightness. So these details of how they organize matter because they're intimately tied to weather circulations and ocean circulations. This is half the motivation. I'm obsessed with low clouds because they're ubiquitous in observations. They have complex organization dynamics in observations. On the one hand, we can simulate the relevant turbulent processes in these high-resolution large eddy simulation models, and those already suggest that maybe they may reorganize with warming. But how that reorganization will interact with all the other things happening in the planet is really difficult to tackle right now. But we should expect physically that it will be linked to changes in circulation for the same reasons any planet's radiation is linked to circulation. So turbulence matters. Now let me give you another motivation that comes from my living in an Earth system science department, which means I talk to people beyond the atmosphere where I was trained, to people like terrestrial ecophysiologists and biogeochemists who opened my eyes to another reason why turbulence matters a lot. Let's talk about rainforests. How will the Amazon rainfall change in future climate? Okay. Well, I don't know if you've heard about this, but there's incredible things that happen physiologically to rainforests as carbon goes up in the atmosphere. You know, on every leaf, there's a little pore called a stomata where the plant photosynthesizes and sucks in its CO2, but it prefers not to keep those open because it also has to leak water vapor out of those pores. And in a carbon-rich atmosphere, plants adapt physiologically because there's so much more CO2 out here, they can photosynthesize at the same rate with a narrower aperture and therefore leak less water. And so at higher CO2, photosynthesis becomes more water use efficient, and this affects the atmosphere. It's a change in the surface energy partitioning. And we can do climate. The great thing about climate model simulations is you can test hypotheses. So on the left-hand side is a projection of how rainfall will change with climate warming. CO2 increases in the atmosphere, the warming, as well as CO2 increases in the land, the physiology. And on the right-hand side is isolating just the effect of the plant physiology. Look in the tropics where the rainforests are, over the Amazon, over Africa, over Indonesia. There's huge rainfall changes. Brown regions are drying, blue regions are moistening in the future. And on the right-hand side, you can see that half the amplitude of that pattern is coming just from the plant forcing. So somehow the plants at the surface are changing the planetary boundary layer in ways that orchestrate these rainfall changes, even independent of global warming. And we can do detective work. Don't bother about all the arrows on here, but you know, we can spend a year really understanding the causality of what's making this happen inside the model. And the ironic news at the end of the day is that the details of how the approximated toy turbulence model want to respond to this plant forcing and move vapor up or down ultimately control its flushing away from the forest and the decrease in rainfall. So me, as someone who obsesses over the details of climate simulation, I start to get worried. To study these important effects of vegetation on regional climate, we also can't escape these uncertain details of turbulence. So that's the other half of the motivation if you care about rainforests. We know that at high CO2 plants become more water efficient. We know this changes surface energy partitioning, and our models tell us that the parameterized, the approximated turbulence plays a major role in orchestrating the predictive water cycle response. Turbulence matters again. So turbulence matters to large-scale planetary phenomena, the amount of warming, the brightness of the planet, but also to details of the regional water cycle. So let's talk about where we stand in doing justice to turbulence in global climate models. Well, on the one hand, it's a really exciting time. For the first time, the world is intercomparing models like this. Different international centers can now produce exquisite simulations that use 1 kilometer horizontal resolution across the entire planet. That's a huge computational feat. And you can just look at the animations. This is a simulation, and it's producing things you might be tempted to think off the coast of California resemble what I showed you in the satellite observations. To be fair, it is producing a lot of very realistic things. Tropical cyclones that look realistic and monsoons that look realistic. But I want to caution you that these tools with 1 kilometer horizontal resolution on the left are great for doing justice to those large thunderstorms you see out your airplane window that might be 5 kilometers across. But they're dubious for these important effects of shallow turbulence. The length scales are 10 times smaller in the both horizontal dimensions, which requires a 10 times shorter time step to resolve them. And you add it all up, and it turns out to require 20,000 times more computational intensity than the thing that we've just become able to do as a community. So that's the computational challenge. We all expect we'll have to wait 50 years for Moore's law to continue doubling the power of computing before we can ever begin to produce simulations that do as much justice to the shallow turbulence of low clouds as we've just begun to do for deep clouds. So this is where we stand in global modeling. We know that the length scales of boundary layer turbulence are sub 100 meter horizontally. We know that compute intensity octuples for every resolution doubling, and even our most ambitious models are stuck near this 1 kilometer horizontal resolution limit. And while we've got sophisticated, there's a whole community that builds sophisticated higher order coping mechanisms to cope with this problem, those parametrizations are always hard to generalize, and you always wonder whether a well-intended parameterization can fail in a new circumstance exposed from climate change simulations that might not have been envisioned by its designers. So where we stand in global modeling is that these unsatisfying approximations of turbulence seem inescapable.
Hi, Mike, would you mind if I ask just a basic question here? So you've laid out this kind of where we are and the the challenge, this incredible 20,000 factor of 20,000 challenge that you're facing. Can you give us a sense of what that means? I mean, in the sense of, you know, just in terms of directionality of the issue, is it that not being able to resolve the structure compared to some like perfect idealized simulation, does that blow up the error bar over 100 years when you're trying to predict things like, you know, temperature rise globally, you know, things like that? Just give us a sense of what that means, just in terms of sort of uncertainty for big picture things.
Yeah, thanks. Yeah, this leads to very large error bars on our estimates of how hazardous my children's future will be. So you can give the same climate models, 20 climate models collected around the country that heavily approximate these low cloud physics. You can give them the same what-if scenario of how we think CO2, aerosols, other climate forcing agents will evolve over the next century. They'll give you wildly different answers. And so there's a spread among the predictions that informs our error bar of the future climate change. And it's a large error bar. And then if you then ask what created the spread across the models, you can do the detective work. You can trace it mostly to what they're predicting about low clouds. So the models, you know, some models predict that, like ice sheets, low clouds will thin and dissipate with climate, exposing darker surfaces, which will amplify global warming. Other models predict that, unlike ice sheets, low clouds might thicken and densify and cover more surfaces with bright patches, which would damp global warming, leading to less hazardous future. And that's, you know, that uncertainty comes from different strategies to approximate and cope with the fact that low cloud physics have not been resolved. And the hope is that with more computational intensity, climate and explicitly resolving, allowing the appropriate equations to govern the dynamics of these low clouds, those uncertainties might come down. Does that help, James?
Yeah, that's perfect. Thank you, Mike.
Thank you. Yeah, sorry for not mentioning that. Okay, but yeah, that's the dilemma. Now looking ahead, okay, let's talk about machine learning. Why is it exciting? Well, deep learning emulation might allow us to get these details in ahead of schedule. There's always a balancing act between how fast the computers are, they get faster every year, and how much justice we can do to the cloud physics. And it depends on how hard the job is. Our job is normally hard. We have to simulate the whole atmosphere's evolution for decades, many, many times for scenario planning. And that means we have to approximate a lot of cloud physics. So for me, when I use superparameterized models, I really idealize the subunits that do the explicit convection. I make them two-dimensional and coarse resolution, and I use small domains, things I prefer not to have to do. But in the machine learning era, if the job changes just to making short simulations of a couple of years that will just mine for their physical essence to train machine learning emulators, then wow, today I can take the same computing cluster and do much more justice to turbulence physics. I can do what I prefer, use three-dimensional domains that are high resolution that begin to capture explicit low cloud formation in ways I find plausible. So that's the big part of it. And there's another technical part of it that I actually think is equally important. Supercomputing itself has been disrupted nationally over the last decade. Transistor density on a chip asymptoted a long time ago. And so for scientists and engineers to get increasingly faster computers, clusters just got bigger and bigger. You got 10,000 nodes, 50,000 nodes. But eventually a physical limit of cooling was reached. The utility says, no, we won't build a power plant that big to cool a cluster that big. And so things asymptote again. And so what's happening now is that unfamiliar new computing architects are emerging that prioritize low watts per flop. And so this is causing new architectures like graphical processor units to dominate the greatest computing clusters in the world. But reprogramming a scientific climate model for those architectures is really hard. And climate models are millions of lines of code. And so our climate models actually can't even take advantage of today's most powerful clusters because of this metamorphosis in computing that's going on. And that's the other allure of deep learning emulation, is because once trained, a neural network emulator is unbelievably portable between lots of different computing architectures. And so this might open the door to accessing machines like this. This is one of the world's most powerful supercomputers owned by the Department of Energy. It contains 4,500 nodes that are full of graphical processing unit computing hardware. So that's the reason to be interested. So now let me tell you an actual research story of trying this. So what we begin with are deep neural networks, which are powerful emulators. They're just high-dimensional regressors. They're curve fitting on steroids that can happen in high dimensions, and they happen to be easy to train with modern GPU hardware, and large data sets. And you see this all around you. Video recognition, image recognition, predictive text on your phone is all being powered by this new tool that's disrupting industry and science, deep neural networks. These are a way of programming that learns from exposure to training data rather than a set of rules. And in our case, we can train them to emulate cloud responses to climate change by feeding in on the inputs, things like from the host climate model, like large-scale temperature, large-scale vapor, incoming sunlight, incoming surface fluxes. And on the output, we can try to predict the things that we normally have to spend a lot of compute intensity predicting. The average convective heating from an ensemble of clouds, the average convective moistening, how clouds as an aggregate, as an ensemble, after all the details on the bulk, move heat and moisture vertically in response to these forces. And we can do that hundreds of millions of times with double precision data by leveraging super parameterized climate simulations. These are this way of climate modeling I mentioned that embeds convective detail inside submodels, and therefore there are clean arteries separating local submodels from host grid cells, and you can machine learn those arteries, what came into the submodels from the host, what came out of the submodels after all of their work. And it's not obvious that a neural network should be able to learn that, because those submodels are themselves contained of partial differential equations with chaotic behavior that are prognostic and integrate over many time steps. So this was an open question when we tried it in 2017. Could 140 million pairs of inputs and outputs harvested from a long simulation of a climate simulation? We did it on an aquaplanet, pretending there was no continents for simplicity, just to test this hypothesis. Could you even fit that type of data with a neural network? It's very unlike image data. And after a lot of tinkering, about a year's worth, it turned out to be, yes, this image shows you the skill of a neural network after it's been trained, assessed relative to a holdout data set that was not used in the training. The y-axis is pressure going up in the atmosphere. The x-axis is latitude going from the South Pole to the North Pole. And these big blue blobs in the mid-troposphere are regions of skill. Over 70% of the variance of the actual cloud resolving model simulations can be predicted by these dumb sheets of neurons. And I was amazed by this. And so quite possibly. And we did some more work, and we tried to implant this neural network emulator in a host climate model, and it behaves actually pretty well. So actually, there's another offline test here. On the right-hand side, you're looking at the predicted global map of precipitation from the neural network relative to what it was trained on in the middle, the cloud resolving model. And on the left-hand side is a standard climate model that doesn't use superparameterization. It has a fairly unrealistic distribution of precipitation. But the middle panel is what we're trying to learn. And if you just compare the right and the middle panels, it's doing remarkable justice to the patterns of precipitation with some issues. It's not capturing the stochasticity and the noise of the real convective system because it can't learn chaos. Neural networks are deterministic, at least this category of them. But overall, I found this sort of skill level really surprising and captivating. And I won't bore you with all the other details in the tests we did, but suffice it to say that we were able to run a neural network powered climate model simulation for the first time that produced appropriate behaviors. And that's gotten me interested in this whole topic. And I was surprised with it. Okay, but it's also exposing to new challenges. I want to spend some time in this talk talking about the interesting challenges. As it's happening around our community. There are lots of research groups at MIT and Oxford and the University of Washington who've been trying similar things in recent years, and we're all trading notes and having interesting conversations. But what do you sacrifice? What's the trade-off here? If we begin to outsource our physics to neural network emulators, what are the consequences? It's skill on the one hand, but maybe it's cheap skill. But could you lose some things? One thing you lose are experimental process knobs. Climate models are a tool where we exploit to further our understanding of complex phenomena, like things how a mixing rate between a convective updraft and its environment feeds back with broader planetary scale climate dynamics. That's a convenient experiment to run if you have a parametrization with a clear knob on it that you can turn the mixing rate. But when the mixing rate has been combined with every other process that was happening in the cloud resolving model inside an uninterpretable neural network, you lose that knob. And so, maybe this is skill, but maybe it's cheap skill that comes with some trade-offs and some loss. Then again, the other thing you can critique is the number of parameters it takes to train one of these neural networks. So it turns out that I think we required on the order of 1 million parameters in our neural network to get a successful fit for this challenge of a problem. Is that helpful? Is that unhelpful? boiling things down to as few parameters as possible is what physicists tend to prefer to do to further their understanding. You know, the cartoon on the right-hand plot, embodies that idea. So you might say it's not unsatisfying to have millions of parameters in a neural network emulator. Then again, now this is a slide I borrowed from my former postdoc advisor, Chris Brotherton, who's built an incredible career building sophisticated parametrizations. But he'll admit that if you look out the airplane window at the actual complexity of actual cloud populations interacting with each other, you know, there could be 20 or 30 equivalently plausible cartoons you could have drawn to parameterize that. And so maybe the degrees of freedom actually deserve this many parameters. I think the idea of what millions of parameters mean in the machine learning area is also interesting. This is a picture from Francois Chollet's book about deep learning, which I really like, that describes that deep neural networks require so many parameters because they try to incrementally decompose a complicated geometric transformation into a long chain of elementary ones. And you can think of the analogy of how would a human go about unraveling a sheet of paper? You know, you probably take many incremental steps to get there, and different humans might take different steps, but they're all equivalently fine paths to the end. And so, you know, even if there could have been a theoretical minimum number of parameters to get from the crumpled state to the uncrumpled state, you know, maybe you don't care if your goal is just to uncrumple the ball. So millions of parameters might be fine. Okay. That's sort of a philosophical problem. Here's a more practical one. Data-driven models like this don't know about physical constraints like energy conservation, and we can see the symptom of that. If we ask ourselves, once trained, does our neural network emulator leak mass or enthalpy, which are conserved quantities in atmospheric thermodynamics? And the answer is yes. Frequently on the order, this is a histogram showing the magnitude of the leaks, more than 25 watts per meter squared of enthalpy can leak out of a neural network. That's unacceptable. Climate change is a 3 watt per meter squared forcing at top of atmosphere. So unless we can find a way to deal with this problem, we're stuck. So I'll tell you another little story about how to physically constrain neural network parameterizations. This is a nice graphic that UCI Strategic Communications made. We had a paper about this recently. This is Tom Buechler's work. He's designed a way to modify the architecture of the neural network to know about conservation laws, conservation of mass, enthalpy, conservation of radiation. And this is a complicated diagram, but let me explain it. On the left, on the right, on the y-axis here, we have skill. Okay, so lower is better, and on the black dots show the skill. And on the left-hand box, we just focus on the left-hand side here. We're looking at a typical unconstrained neural network that doesn't know about conservation laws, and that's its skill. It's pretty good. We like that number, that black dot, just north of 100 watts per meter squared. But the problem is it's got big energy leaks that are also on the order of 100 watts per meter squared. Now, Tom has a way to do, he tested 2 strategies to force energy conservation to happen. The user of machine learning is in charge of the optimizing function that the machine learning is required to learn. The machine learning only learns what you tell it to. And so you have the freedom to bake in a penalty term in that loss function that penalizes conservation of energy violations. And Tom tried that. And you can see in this middle box here that the good news is that the leaks go down, the blue dots go down. Okay, so we're getting less energy and mass leaks. But the bad news is that the black dots go up again. This is a log scale. So there's a trade-off. You can penalize conservation, but then you also get less skill. And you need the skill of the fit to behave well once you embed the neural network in the host model. So on the right-hand side is Tom's solution. He found a crafty way to enforce internal to the neural network, upstream of its optimizer, this rule, this set of rules that things have to be constrained. And we were worried that we might see the same trade-off, that we wouldn't get as good skill as the unconstrained network. But the black star here, you can see, is at the same place on the y-axis as the black dot on the left, which tells us we can solve the problem of energy conservation. A year and a half ago, I was worried it might be a deal breaker for this technology, but it seems there's a few approaches emerging that can solve this issue. This is a way of incorporating knowledge into your machine learning. The other question is how to generalize your physics. So, you might be attracted to the idea of training emulators of physics on observations of current climate and hoping they might predict something about future climate. But is that really possible? Neural networks are better at interpolating between known things than extrapolating to new conditions. And this is another place where some combination of physics and machine learning can be helpful. So one simple, crude thing you can do is just convert an extrapolation problem to an interpolation problem through physical normalization. So this plot here shows you a problem happening in when a neural network trained in a cold climate is tested in a warm climate. So the truth is the black line, and the neural network is failing spectacularly to predict the truth because it was never trained on the warm climate. But Tom can make a simple modification to the input vector by choosing to phrase the moisture coming into the neural network rather in units of specific humidity, which changes with climate because air can hold exponentially more water vapor as it warms, to relative humidity, which is a perfectly fine way to express moisture content as well, but happens to be bounded by the same values of 0 and 100% in any climate. And just that one little modification to the input vector can go a long way towards fixing these out of sample extrapolation problems. So I feel like this is a whole area where more work is needed to understand to what extent can we physically, strategically renormalize the inputs and outputs of these emulators to shield ourselves against extrapolation error. Here's another problem. This one we're working on actively. There's a bit of a reproducibility crisis. That shiny result I showed you where we trained a neural network and it worked well and produced a neural network powered climate model has been hard to reproduce. It turns out more often than not, despite your best efforts to train one of these things, when you implant it in the host model, the whole simulation blows up spectacularly in an unpredictable way. And a lot of us are thinking about this and talking about this issue. So what do you do? I think it's endemic of like lots of people working in machine learning these days. There's finicky machines that might need, and I think we as a community have to decide what are the tests of physical credibility that would lead us to accept a neural network. So that's one thing we can do. And this plot is sort of showing one of the tests of physical credibility that we seek. We can expose the neural network once trained, or expose a family of neural networks to some tests. Ask them, what happens as I increase the moisture of the troposphere on the input, where I have an expectation, as the blue line shows on the right, that as you increase the moisture towards the darker blue colors, the altitude of the convection increases and the magnitude of the convection increases. So you can perform these tests, you can define these tests, and then ask your neural networks if they pass them, and select, as a scientist, only those neural networks that pass the tests that you deem important. And so this is a conversation we're having now is, what are those tests? Jin.
Mike, can you clarify what you said, a lot of times you run the models and it blows up. And can you sort of clarify what that means? Is the temperature skyrockets, it just stops running and grinds to a halt? Like, what is it that happens?
There seems to be a family of failure modes, and I don't think they've all been assessed, but many things can happen. Here's an example of one, though. So what you're looking at here is a map, latitude on the y-axis, longitude on the x-axis. And what we're looking at is the specific humidity tendency that comes from convection, how convection is redistributing moisture. And this should have like a geophysical structure. We should see weather patterns here where there are clouds that are busily redistributing moisture. But what you can see is an unphysical bullseye that looks like a target in the top right of the plot. And that's a ringing that looks like an explosion. And so the system has found a way to create a crazy explosion in this one corner of the atmosphere. But these explosions all take different forms and they happen in different places. And I don't think we know exactly what causes them or what can reliably limit them. But we're starting to find that out. That's kind of where we're at. There's we have a couple papers where there's some tricks you can do to reduce the frequency of occurrence of this happening. But it's not clear whether there's a reliably reproducible way yet. And so this is a really active research frontier. And also sorry, so have you implemented the sort of making sure they obey energy conservation, et cetera, in these models? So even after you sort of make it physically, rigorous or whatever, basic physical laws are obeyed, you're still getting this kind of runaway bullseyeing or whatever. It hasn't been explicitly tested, but I expect it will. So we got a hint at that. One way you can foresee that is by, even without going to all the work of embedding the emulator in the full climate model, you can expose it to a generalization test and see how bad it generalizes, which is one way to hint at how robust it will be to problems once embedded. And I think the problem is that the degrees of freedom of the output vector are on the order of 100 scalars that it's trying to predict, but there's only 4 conservation laws. So such a small fraction of the output space is based on conservation laws. There's still a lot of degrees of freedom for just imperfections in the fit to happen. I got it. So since we're talking, let me ask a question from Brad Jenkins. Sure. He says,
Are a small number of areas or conditions highly influential to Earth atmospheric systems? Areas to use intensive turbulence physical modeling while using neural networks for most of the rest of the models? I guess he's asking about.
Great question. I love that question. Yes, yes, totally. Certain subregions of the atmosphere deserve more computational intensity than others, and I don't think our global modeling field has caught up to the software designs that could do justice to that fact. But that's another. We could have an hour conversation about that. I'm working on that separately, independent of neural networks. There's ways to devote more computational intensity to subregions that deserve it. Great question. Yeah. Right. Okay. I'm going to skip a couple slides here. Okay, but yeah, I think these sort of existential issues of instability are asking important questions like, can past successes be reproduced? Are these instabilities controllable? Does offline neural network skill from a holdout validation data set even relevant to predicting its online coupled performance? And one barrier has been super low level, that there's just not software tools to answer these questions. Tuning neural networks is painful. You have to do hundreds of tests and twiddle the architecture of the neurons and the optimizing algorithm that chooses how you go down the loss function. And translating neural networks once trained into Fortran kernels is actually hard. And so this is a place where we had a fun collaboration with UCI computer scientists to just build some, or to learn some of the tools that they use in image recognition. There's an in-house package called Sherpa here that takes the pain out of auto-tuning neural network parameters. That's been life-changing for us. And then we built a new tool together too called the Fortran Keras Bridge, which simplifies the union of these two different programming languages where machine learners like to work in Python, but astrophysicists and chemical modelers and climate scientists frequently rely on Fortran code that's pushing computational limits on clusters. And so this new software has allowed us for the first time to even begin this process of testing dozens of candidate neural networks in prognostic mode. So I'll advertise the bridge and point out that Pierre Baldi and ICS and a student, Jordan Ott, through an NSF graduate student program that we have that can facilitate the union of physical science professors and CS professors, has been really productive in producing this new package. Lots of people seem to be downloading it in different disciplines that also would like this capability. And for us, it's allowed us to sort of map out the first results from actually testing a biodiverse candidate of neural networks, hundreds of candidate neural networks inside of a climate model. So this cloud of points illustrates hundreds of different tests. And the y-axis shows you a simple metric of failure. How many time steps do you run before crashing the model? And you can see there's a relationship here. The blue dots tend to run longer than the orange dots. So we've learned that the choice of the optimizer algorithm that you use to train the neural network really matters. You find more stable neural networks when you use a particular optimizer for our problem. I'm not going to talk about this figure, it's too complicated. But I think this new software is starting to tell us what it's going to take to reproduce past success. One thing is really exhaustive hyperparameter tuning using automated tuning packages that really take advantage of big GPU clusters to explore lots of candidate fits. And this is beginning to help us reproduce the initial shiny result. But it's also opening our eyes to the work that's involved and the dangers that lie ahead. So while many candidate neural networks drift to unphysical attractors, even if they seem to run stably, there is a hint that offline validation skill can predict online performance. So maybe the future is just really like brute force hyperparameter tuning. So I was worried for a while that we wouldn't be able to reproduce the original result, but I'm more optimistic now, and I'm really interested in learning more about what the computer scientists use to beat image recognition competitions. Okay, and I see I'm running out of time, so I think I'll make this, let's see what we do here. But I want to resurface for a moment and just point out these threads of research that are showing that deep learning does have breakthrough potential in our field. To me, it's already surprisingly good emulator of deep moist turbulence. And I'm already convinced that even short super parameterized climate simulations, which are, the governments that do IPCC climate projections do not include super parameterization, these embedded cloud resolving models, because it costs 100 times more computing power than the normal business of climate simulations. But these neural network emulators are starting to make them much faster to run, to create efficient emulators with the same benefits, but that crash a lot. So the issues of instability are yet to be resolved. And I'm optimistic. There's a few strategies emerging for how to control these instabilities. I'm optimistic we'll solve it. It also has potential for interpreting and intercomparing these dynamical systems. I don't think I'll have time to talk about that here today, but our community has really only scratched the surface. Everything I've described is using the neural network as an engineering tool to outsource some calculations we would have done otherwise. There's a whole other thread of work that you can do, which is neural network assisted inquiry into the dynamics themselves. The dynamics, the output of climate models as they become high resolution are increasingly overwhelming for the human to analyze. So having a AI unit that can help you avoid your own human predilections and assumptions you make for how to deal with that data to in a self-supervised way describe it is another interesting area. But I think right now on the engineering front, we have a license to start wondering what else might be emulatable. What else are missing physics in our climate models that we know we should be doing justice to? We wish we could. If we had infinite computing resources, we would. Things like in-cloud chemistry, explicit chemical calculations coupled to dynamics. If you want to study how ozone processing in the troposphere leading to health hazards at the surface will interact with climate warming, you'd prefer to have a climate model that also is very computationally intensive on the chemical side. That's species level ecosystem dynamics. There's people in my department that would love it if climate models included populations of plankton and different species of plankton that can explicitly interact to sort of map out how the changes in ocean circulation interacting with the changes in nutrient supply will play out across species ecosystem dynamics in ways that ultimately affect the overall carbon cycle of the planet. There's actually fundamental mathematical work I haven't told you about here, but it's another area I'm really excited in. At the very heart of weather models and climate models are solvers of partial differential equations, where we try to numerically approximate the solution of an analytical equation. And we have, as a community over decades, used a set of discretizations of ways of estimating numerically those solutions. But there's a new line of work coming out of Harvard that just asks a neural network to come up with the best discretization aware of the high resolution solution that's producing really compelling convergence properties that might be another way to end run ourselves to higher resolution ahead of schedule. Right, and I'm going to skip part 4 because I've totally run out of time as I thought I might, and just maybe share one last picture with you. No, I haven't told you the story, but if you're interested, we can talk offline. I do want to acknowledge that interpretable deep learning is here. Neural networks are no longer black boxes. There's tools to visualize their decisions. This is an area I'm moving into. I think it's going to be a game changer in our world. And that even these seemingly engineering acts of emulation are turning to have some come along with them for free, some beautiful summary diagnostics that in the act of emulating, you realize you've also created a diagnostic that summarizes complex interactions in a new way. So yeah, I'm especially excited by the idea that neural networks can be used for more than just prediction, and that the science of might be what the network learns soon rather than just a prediction. So I see I'm out of time, so I think I'll pause there, and thank you so much for your time and your questions, and I think we have time for some more.
Mike, thanks so much for that. Let me just invite folks to go ahead and use the Q&A box if you have questions. I'm going to, I'll ask a couple that have popped up. So Gary is asking, can a statistical test, I guess the validation tests that includes these really high dimensional machine learning extrapolations be valid? That is, if you're using many, many trials and many, many parameters, what's the, how do you test it given, if you have that many sort of free parameters? I think it's the general gist of the question.
That's a great question. It's sort of like an unsatisfyingly empirical art that I don't think has agreed upon manuals of statistical tests so far. Yeah, and it's I think one of the reasons the technical debate around machine learning is so vigorous. It's like we really have to exchange our strategies that lead to anomalously good fits. I mean, there's things you can do, right? I think it is important to be statistical in this work. I think one should never be in a situation where you're training a small number of neural networks, because it seems very important to assess large ensembles of candidate fits to find general principles and to even guide ourselves towards what has reproducible benefit. So in that sense, I think like statistical tests are vital, but I hear your point that the free parameter space of neural networks is very large. But that's part of their success in achieving things like near human level image recognition. So it sort of comes along for the ride.
I have sort of a, I guess, related question. So to what extent is sort of remote sensing data used to sort of test and improve climate models more generally? Is that an active effort?
Oh, it's absolutely vital. So the issues that we have with low clouds or with other defects of our climate models are all informed by comparing their predictions routinely to satellite observations. So I didn't mention observations much in my talk, but my obsession with being more explicit and finding a way to outsource these physics to neural network emulators is built on a history of comparing expensive simulations that did include those physics to airplane observations, field observations, and satellite observations, where there is some consensus in our community that the resolution really does buy you something that even our best parameterizations can't. Did I answer your question?
Yes, thanks a lot. And here's another question. How well understood are the PDEs arising in the climate models from a mathematical perspective? Are they well posed? Are they, do they have unique solutions, or are there stability solutions established? Are there singular solutions, et cetera? I guess it's sort of the basic equations that you're solving.
Yeah, I mean, there's a spectrum of really fundamental ones that are rock solid. Like, at the heart of the climate model's dynamical core is a scaled version of the Navier-Stokes equation, the fundamental equation of fluid dynamics. But it's scaled to under the approximations of a shallow layer of fluid on a rotating coordinate system, where some terms of the Coriolis parameter you can convince yourselves are asymptotically negligible. But there's so many PDEs inside of a climate model. In the heart of its cloud thermodynamics and microphysics routines, there's a whole different set of PDEs where you could ask some questions about that. I mean, that's like a half-hour conversation. I love that question, but yeah, maybe we should have a coffee and talk about it. But there are other phenomena though that we just don't know the equations, like the microphysics, ice microphysics. The details of the geometry of an ice crystal actually really matter to its interaction with long-wave radiation. NASA's still flying airplanes to even collect the samples to inform that. And so on the remote sensing front, there's a whole subcommunity interested in machine learning as a way to sort of build Bayesian inference models that accept the structural uncertainty of our current formulations of PDEs, and yet somehow constrain them against the observations that we have in an automated way. Yeah, I'll stop there, but that's a fun question. Yeah.
Thanks. Let me just invite other questions if people have them. I have another one for you, Mike. This last point you talked about as sort of the black box issue. And I think, physical scientists in particular are really interested in learning the science, and they want to know, what's in the head of the black box. They don't want the black box to know, they want to know the answer. And I know that there's been a little bit of progress in particle physics recently of sort of cracking open the black box and sort of understanding the physics of what's happening there. So I would be really interested in, hearing a little bit more from your perspective on that and the future for climate models in terms of, making the box a little less black in terms of knowing what's going on inside of it.
Sure. Well, I'll take the excuse to share a couple more slides then, if that's okay.
Sure.
Yeah, I think that's a really important topic. Let me come back to this one. Okay, so here's, I think we're in the beginning of this in our field. So I'll show you first some work. I want to advertise this work, Griffin Moore's. This is another MAPS fellowship that's united our group with a different computer scientist who does video compression. So part of understanding a high-dimensional system is finding a way to reduce it down to minimal dimensions. And that's also an engineering act in video compression. So you can use neural networks for this. A different class of neural networks that does self-supervised categorization. This is not an engineering exercise. This is an exercise that our students took to take millions of samples of the details of turbulence, the configurations of updrafts and downdrafts happening at different locations across the planet, and asking an unsupervised machine learning algorithm called a variational autoencoder to cluster it in a minimum number of dimensions. And conveniently, he found he could do it with 3, which lets us see it with the human eye. And the clusters of the latent space indicate 6 distinct classes of convection that the machine learning algorithm thinks ought to be distinguished. As an atmospheric scientist, I'm very happy to see these be the clusters that were discriminatable, because there's a history of heuristically dividing clusters with similarly distinct vertical structures on the left. But I feel like it's taken a year to just understand how to do this. because there's an art to training these variational autoencoders, and I'm not sure yet that we've found anything really provocative that would generate a new hypothesis that would be inconsistent with my understanding of how we conventionally cluster this sort of data. But I'm excited that we might, and I know in other fields you can. So for instance, in animal cognition of sound, you can take audio data and you have your human ideas about how to cluster it and which animal vocalizations you think are distinct. But the latent space of variational autoencoder compression of such data has disrupted that field and generated new hypotheses. I'm waiting for that to happen in our field. One thing that has happened in our field that I think is really interesting, not in our group, but a close friend of mine who's also a co-lead of this national working group, Professor Elizabeth Barnes at Colorado State, got really creative with her neural network. She chose temperature maps, annual temperature maps like this that show the climate anomaly of temperature relative to some baseline, and fed them in to the input of a neural network tasked only to predict what year it was. Not because she was interested in that prediction, but she wanted to ask if the neural network could become skillful, then it would have had to have found some signal of externally forced climate change in this temperature map. And so here's the setup: temperature maps in, year estimate out, simple neural network. And the whole point of it is to then run one of these interpretable methods backwards. So once you have some skill, you can then use something called layer-wise relevance propagation, which, for instance, computer scientists learn to decide how image recognition neural networks figured out it was a cat. Sometimes they get fooled by a fence behind a horse and learn to associate fences with horses. This is a way to see that. In our field, it's a way to see, hey, where in the world was temperature actually predictive of externally forced climate change? And on the left-hand side is the year 2000. You can see the biggest temperature anomalies are in the Arctic. Like, that's polar amplification. We expect that. You might think that's where the most reliable information about climate change would be because the signal's biggest there. On the right-hand side is the relevance map from the neural network, which actually fixated on the southern hemisphere, because at this period of externally forced climate change, the ozone hole's recovery was forcing a southward migration of the polar jet stream that was a better indicator of externally forced climate than the Arctic. So this is, again, something that's just starting to happen in our field. It's only been explored in low dimensions. I think its highest potential, like anything for neural networks, will be in the overwhelmingly high dimensions that we don't know already have ways to do this stuff with. But, yeah, a couple threads there, but
wow, that's fascinating. And I'll just sort of say, I think that kind of exploration is starting to happen in a lot of different fields right now. And it's just the sense that this wave is breaking, and it's not clear exactly what's going to happen, but it does seem like there's just a lot of positive directions here, and probably ways that even you can't predict, I'm guessing.
Yeah, I think no one knows where we're going to be in 2 or 3 years.
Let's try to squeeze in one more question here. So it says, how do you understand the success of deterministic functions like neural networks to capture chaotic features like turbulence?
Great question. Yeah. So first off, they shouldn't be, right? They can only ever capture the deterministic component of convection. And because in my context, we're training on the statistical average properties of a convective simulation that are received, like, the aggregate poll statistics that are received by the pollster. It's a little more deterministic and well posed, but not perfectly. And you expect to lose some of the chaotic part. There are other architectures, however, like conditionally generative variational autoencoders that ought to be able to learn the conditional dependence of the distribution. There are Bayesian neural network methods that can do justice to the range of possible outcomes due to chaos. We haven't had experience, those are much harder to train, but I am aware of work happening down at UCSD where those sorts of architectures are being used to good end to bias correct numerical weather prediction models in ways that are sensitive to the chaotic component. So yeah, there's useful tools to try if you want to do justice to the chaos. For my particular engineering niche application, it was safe to ignore it. Yeah, but great question. Yeah, another topic of interest.
Well, thanks so much. Well, let me thank everybody for joining us today. I think we're out of time. And Mike, thank you so much for this wonderful talk. It's great to hear from the sort of forefront of research and really clear. So thanks so much. I hope everyone has a great summer. And I hope the next time we do this, we're doing stuff in person. So long, everyone. Bye, Mike. See you next time.